For section 6.2, we're looking at the trig of right triangles. Most of this should hopefully be a review from geometry, but it might have been a while since you've done this. First thing, when we're talking the trig ratios, we're thinking back to SOHCAHTOA, which make sure you know how to spell that, because that tells me the trig functions. I just remembered how to spell it. Some students, though, have taught me that they learned it as some old hippie caught another hippie tripping on acid. So whatever works, whatever you need to help you with it. Remember that when we're looking at a right triangle and we're looking at an acute angle theta, we have the opposite side, the adjacent side, and the hypotenuse. So opposite side of the triangle, adjacent is the side, the leg that's next to it, and hypotenuse is obviously the hypotenuse. So sine, according to SOHCAHTOA, is opposite over hypotenuse. That's what the OH stands for. Sine is opposite over hypotenuse. Cosine, CAH, cosine is adjacent over hypotenuse. And tangent is OA, which is opposite over adjacent. Now, those are the three main ones. The next three are the reciprocals. And exactly what a reciprocal is, we flip the fraction. Cosecant is the flip of sine. So if you might want to make a note that cosecant is 1 over the sine. It sounds like cosecant should go with cosine, but it doesn't, so you got to be careful. Cosecant goes with sine. So if I flipped opposite over hypotenuse, cosecant is hypotenuse over opposite. Secant actually goes with cosine. It's 1 over the cosine. So if I flip that, I'd have hypotenuse over adjacent. This one, at least, the last one actually sounds correct. Cotangent is the flip of tangent. I would take the reciprocal, and it's adjacent over opposite. So for number 1, we just want to find the trig ratios of our angle. That's angle alpha. Alpha kind of looks like a Jesus fish. That's alpha. So first thing, I don't have all 3 sides. So I'd have to do some Pythagorean theorem to figure out my missing side. So 8 squared plus 12 squared. If you did that, you would get 208. Then I'd have to take the square root of that. And if you factor tree that down, you can simplify that down into 4 root 13. So now that I have all 3 sides, I can find all my trig ratios. So I'll start off with the sine. So it's always this trig function angle. So sine of alpha is opposite from alpha. So the opposite side of alpha would be the 8 over hypotenuse, which is 4 root 13. The 8 and the 4 can reduce, so I can just call this 2 over root 13. And now you were probably trained to rationalize that denominator. You may have been taught, oh, we can't have square roots in the denominator. Yeah, we can. It's okay. I'm fine with that. Sometimes we will rationalize denominators just because it's more common on some stuff, but for this, I'm not worried about it. I'm going to go ahead and do the cosecant now, because I know that's just the flip of sine. So if I just take the reciprocal, I'd have root 13 over 2. All right, the next one would be the cosine of alpha. That's going to be adjacent to alpha. The adjacent side is the 12 over the hypotenuse, which is 4 root 13. 12 and 4 can reduce, so this can turn into 3 over root 13. Now that I have the cosine, I'll do its reciprocal, which is secant. That would be root 13 over 3. And the last one, tangent, or the last ones, tangent, and I'm running out of room, so I'm going to go ahead and do it somewhere up here. Tangent of alpha, tangent is opposite over adjacent. So again, it all starts from the angle alpha. The opposite is 8. The adjacent is 12. That can reduce down to 2/3. And therefore, the cotangent of alpha is 3/2. So just practice remembering what the trig functions actually mean. Number 2, same type of problem, except that I did not give you the triangle. So we're going to draw one out. And this will happen a whole lot in this class, where I give you, ooh, that's a terrible triangle. I give you one of the trig function values, and you have to find the other ones. If I give you one of them, you can find all the other ones. So let's just say that this angle here is this angle that I'm looking for. That is beta, by the way. Looks like a bee with a little tail on it. So that's angle beta. Got my right angle. Now, I'm being told the secant of beta. Remember what secant means. Secant means hypotenuse over adjacent. It's the flip of cosine. So I'm basically telling you that the hypotenuse is 11 and the adjacent is 6. Or at least they reduce down to that. They may not actually be those numbers, but they reduce down, so it's good enough. Now this is similar to the previous problem. I need to get my missing side. So if I do Pythagorean theorem, I'd have to do 11 squared minus 6 squared, which is going to give me 85. And if you square root that, it doesn't really break down at all. So my missing side is root 85. So root 85 is definitely bigger than 6. So I did not draw my triangle correctly, but who cares? Doesn't matter. Okay, so the sine from beta would be the opposite, which is root 85, over the hypotenuse, which is 11, which means the cosecant is the reciprocal of that, so it'd be 11 over root 85. I was already given the secant, so I just need the cosine here. So I'd flip the secant and get 6 over 11. For the tangent from beta, it's opposite, which is root 85, over adjacent, which is 6, which means the cotangent would be 6 over root 85. So only difference on that problem was that we had to draw the triangle ourselves using a little given information. Now we're going to get into the special right triangles. And hopefully these come back to you from your geometry days. But we have 3 special angles, 30, 45, and 60. And their corresponding radian measures are pi over 6, pi over 4, and pi over 3. We'll get more into those radian measures in the next section. These are special angles because the right triangles they make have very special properties with their side lengths. Their side length ratios are nice numbers, or nicer numbers. So on a 30, 60, 90, for example, a 30, 60, 90, I want you to notice that the hypotenuse is double the shorter leg. The long leg is root 3 times the shorter leg. That's going to come up in the next problems in a little bit. On the 45, 45, 90, well, both legs have the same length because those angles are the same. And to go from a leg to the hypotenuse, I multiply by a root 2. I times by root 2. So we'll use that in just a little bit, but for now, let's just use the side lengths. So if I'm starting with my 30-degree angle and I want the sine, so from my 30-degree angle, the sine is opposite. So the opposite of the 30 is 1 over hypotenuse, 2. The cosine is the adjacent to the 30. The side adjacent is root 3 over hypotenuse, which is 2. Now for the tangent, it would be opposite, and I'm going to do this off to the side, opposite over adjacent, 1 over root 3, which I am going to rationalize that. The only reason I'm going to do that is because you typically see a written rationalized. So if you remember to rationalize, I times top and bottom by the radical in the bottom, and that would give me root 3 over 3. That's what we typically see for tangent. If I jump to the 45, I don't really care which 45 I pick as my reference angle because they're the same. I'll stick with this one. Opposite over hypotenuse for sine would be 1 over root 2. Which again, if I rationalize that, if I multiply top and bottom by root 2, that would give me root 2 over 2. And again, I'm rationalizing it because we usually see it rationalized. The cosine for the 45, the adjacent over the hypotenuse, would be the same thing, root 2 over 2. The tangent on the 45 is even easier. From the 45, opposite over adjacent, well, that's 1 over 1. So it's just 1. Back over to the other triangle for the 60-degree reference. Sine would be opposite over hypotenuse, so that's going to be root 3 over 2. Cosine would be adjacent over hypotenuse, so that'd be 1 over 2. Tangent would be opposite, root 3, over adjacent, which is 1. Root 3 divided by 1 is just root 3. You will become very familiar with those numbers if you're not already. We're going to be using them for about the next 7 to 8 weeks. On this next group of problems now, we're using the ratios that we talked about. This is a special right triangle on 3A because I have that 30-degree angle. So I know it's a 30, 60, 90. According to the rules, to go from the short leg to the hypotenuse, I multiply by 2. It's double the length. Well, therefore, if I want to backtrack, I'm just going to divide by 2. So x has to be 25 over 2, or you could say 12 and a half. To go from the short leg to the long leg, you multiply by root 3. Well, I have the short leg. It's 25 over 2. So to get the long leg, I'm just going to times 25 over 2 by root 3. And all I'm going to do then is just stick a root 3 on it. And it's done. I did not need to use a calculator. I did not need to use Pythagorean theorem. Since it's a special right triangle, I just have those numbers. Okay, letter B is also a 30, 60, 90. Let's see what I'm given. I'm given the longer leg this time. Again, to go from the short leg to the long leg, it's multiply by root 3. So logically, to go from long leg to short leg, I would divide by root 3. So x must be 31 divided by root 3. And I'm not going to rationalize that because it really wouldn't clean anything up. Once I've got short leg, to go from short leg to hypotenuse, it's multiplied by 2. I've got the short leg. It's 31 over root 3. So I'm just going to double that and get 62 over root 3. So again, I just took the short leg and I multiplied it by 2. Again, no trig needed really, no calculator needed, no Pythagorean theorem needed. Letter C looks at the 45, 45, 90. The only rule with that was to go from either leg to the hypotenuse, we multiplied by root 2. So to backtrack, I'm going to divide by root 2. So, and this will be for x or y. So x and y are the same, and it's going to be 12 divided by root 2. Now on this particular one, rationalizing the denominator actually will make it simpler. And if you're going, well, how do I know when to do that? Well, just ask yourself, will things reduce in the end? So if I multiply top and bottom by root 2, I'd have 12 root 2 over 2. And again, I was kind of looking ahead and I could see that I could reduce the 12 and the 2. And so this becomes 6 root 2. Just simplify it down a little bit. And again, that's both x and y on that one. For number 4, these are some strange looking expressions, but we will see them later on in the semester. So we're kind of getting a feel for them here. If you go back to the table, we found that the cosine of 30 degrees was root 3 over 2. But now this is being squared. According to our table, the sine of 30 degrees is 1/2, and that's being squared. So if I square both of these, root 3 squared is 3, 2 squared is 4, 1 squared is 1, 2 squared is 4. I end up with 2/4, which is 1/2. So that weird looking expression is actually just a half. Letter B, the angles are in radians, but again, if we look to our table, the sine of pi over 3, that's a 60-degree angle. That's root 3 over 2. The cosine of 45, which is pi over 4, is root 2 over 2. The sine of a pi over 4 is also root 2 over 2. And the cosine of a pi over 3, which is a 60-degree angle, is 1/2. Again, this looks like a weird expression, but this is going to come up later. That's why we're doing it. So looking at this first group, if I multiply those, I am allowed to multiply radicals together. So that will be root 6. On the bottom, I multiply and get 4. On the other group, root 2 times 1 is just root 2 over 4. Now, I was allowed to multiply radicals, but I cannot subtract them. I cannot really do anything with this. All I can do for a final answer is just group the numerators together and call it root 6 minus root 2, and it's all over a 4. Again, I cannot subtract root 6 minus root 2. Okay, we'll do the rest of this on a separate video.